Welcome to the Data Standard Experience. I'm your guest host for today, Gideon Rubin. I'm the founder and CEO of Pandio. On our show today, we have Sam Anthony, the CTO and co-founder of Perceptive Automata. Today, we are speaking about the missing piece for autonomous driving. Welcome to the show.
Thanks for having me.
Great. I'd love to hear a little bit more about your background, if you wouldn't mind starting there.
Sure. So Perceptive Automata came out of a bunch of research projects that my co-founders and myself did when I was a grad student actually at Harvard in the Vision Sciences Laboratory at Harvard. My background is kind of a stint as a computer hacker, which we can talk about if you really want to. But after that, my background is before grad school was in web development and web applications. And when I got to Harvard, what I was working on was doing careful psychological experiments, so careful human behavioral experiments at web scale. And this is something, people talk about Mechanical Turk, and that's kind of a way you can do this. But what we pioneered was really taking seriously doing good, careful vision science experiments. And what my co-founders, Dave Cox and Walter Shire, and I realized was that what I was doing with these experiments was happening at a scale where you could start thinking about using it for machine learning. And that led us to kind of a follow-up realization that the way everyone else did machine learning was really missing a trick, because the way everyone else does machine learning, they think of the labeling as just this kind of like noisy process that happens in advance where you're trying to get your training samples, your things that you're going to feed to your machine learning model, tagged with like a fact about the world. And what we realized that process of labeling was really, in many ways, exactly the same as running a psychological experiment, except in a psychological experiment, you can learn much, much more about how people look at the world. So we kind of combined these insights from computer vision and from human behavioral science and ended up with an approach, with a methodology where that methodology is capable of building machine learning models that will answer questions in kind of the specific category. And the specific category is things that people are effortlessly good at and computers are not good at. And so that's a pretty useful, a pretty interesting set of problems. And so that's kind of where we started. And then after quite a bit of iteration, we got to the problem that we're solving with Perceptive Automata, which is understanding humans in the world from the perspective of autonomous vehicles and other autonomous robots.
In graduate school, was that your first foray into behavioral science, or had you been studying that earlier?
I studied it in undergrad. So I had a super weird, like totally not scalable career path. I directly out of high school forewent college because that was the first .com boom. And I was like, I'll just go make a lot of money doing, they'll pay me how much to make a web page. And so I did that, and I kind of moved through tech and had kind of an initial career in tech for about 10 years. And I left that because it felt like the work that I was doing building web applications was getting commoditized, and went back to college and had the chance to sort of pick between the University of California campuses. And the way it worked, I was transferring into those schools. So I had to pick a major to transfer in. And at every UC campus, except for one, I said I would major in math. And then for whatever reason, UCSD, I was like, I heard their cognitive science program is pretty good. I'll put down cognitive science on this one. And I got in, not everywhere, but almost everywhere, and realized I absolutely did not want to be a math major. And so I ended up in the cognitive science program at UCSD, and everything kind of flowed from there.
Nice. Yeah, UCSD is actually down the street from us. I'm in Carmel Valley.
Oh, excellent. I'll tell you what, having moved back to Boston, I have regrets about the weather difference.
Well, I did the reverse. I went to college at Brandeis University, and my brother was at Tufts. So I spent some time in Somerville as well, but I grew up in Arizona. So I went from Arizona to Boston, and I knew,
oh boy,
I didn't want to be in Arizona. And then I knew I didn't want to be in Boston. Yeah. So I'd love to get in a little more about what you're working on now. So can you tell us a little bit about the black box metaphor and how this relates to what you're doing?
Absolutely. So what our system does is our system allows an autonomous vehicle to know what's in the heads of pedestrians. And that's like a weird thing to say, right? So because what's in my head, well, it's in my head. You know, there's not a telepathy, right? How are you going to figure that out? But we as humans, we're very, very social, and we're very good at social reasoning. So when we look at another human, we very quickly come up with a whole set of inferences about what's in their head, like what they're thinking, what they want, and whether or not we're right in some absolute sense, we're right enough to act on it and for it to lead to social behavior, right? By contrast, when you train a traditional machine learning model, what that machine learning model is doing is it's trying to extract a mapping between a set of pixels and a set of numbers. Where that mapping comes from, you don't care. It's irrelevant. What you're really trying to do is you have some mapping, and again, this goes back to the training process. In your training data, you have a whole bunch of images and they map to a whole bunch of numbers. And let's say that mapping is created by a black box, because for all intents and purposes that those people think of it. And then you learn what mapping goes with what. Then you see a pedestrian in the world and you're like, okay, well, which black box corresponds to those pixels that I'm seeing out in the world? So one way to think about this is you take that black box, you put it on top of the pedestrian, and that black box spits out these numbers, and those numbers are what you can know. I think probably it's already apparent that there's a pretty big difference between those approaches. And fundamentally, when you're training a machine learning model, if you are agnostic or if you don't care about where the mapping between the images that you have and the labels comes from, then you're kind of locked in. Like you can have a black box that spits out more numbers. You can have a black box that's, tells you this is what the person's skeletal pose looks like. This person is carrying a phone. This person, all kinds of external things about the person that are more or less helpful. But what it's impossible to do actually with traditional supervised learning, with traditional machine learning, is to make a useful inference about what's in that person's head. So when we say that perceptive automata removes the black box, that's what we mean. By training machine learning models the way we do, we can answer questions that are the kind of questions a person would answer, that are questions about what's in that person's head. And so when you do that, all of a sudden you don't have a bunch of black boxes spitting out numbers, but you can say, okay, wait, these are people. These are people with intentions and goals and awareness, and act around them based on that information.
And so at the end of the day, are you really just looking at essentially people and their actions and then figuring out those actions are leading up to certain other actions? Or because you talk about being in the person's head, like how are you connecting it to actually what's in their head versus, their actions? Because I guess that's the ultimate output that you want, is a better understanding of what their actions may be, based on what's in their head, right?
Yes and no. And I think to turn that around, if you think about when you're driving and you see someone standing by the side of the road and you say to yourself, oh, they're waiting to see if they can cross in front of me, how do you know that? And so the answer is that we as people, we're using visual features of the pedestrian. We're using things about how somebody looks, right? We're not talking to them. We're not just making a guess, but we are so good at using those visual features that it happens essentially unconsciously. And what really pops into our head is, well, this is what's in that person's head. So when we train models, what we want to do is we want to have models that, first of all, pay attention to all of those visual features that humans use but are unaware of using. So we want to capture all of those unconscious visual features. And then the question we're answering is really, it of course correlates to actions that the person's going to take, but it's really not quite about actions at all. It's very directly about what's in that person's head. And probably the best way to think about it is we answer the question, let's say there's an autonomous vehicle, there's a self-driving car, it's approaching a pedestrian. And the question we answer is, okay, if there were 500 people sitting in this car and you ask them to take a vote about whether that person wants to cross the street in front of you, what would the distribution of their responses look like? So it's it's predicting the wisdom of crowds answer to what's in that person's head. And it turns out when you're driving a vehicle, that's the question that you need to answer. I'll give you an example. Let's say you have an autonomous vehicle that doesn't have this ability, and there's a person standing by a crosswalk, and that person is motionless. And so the autonomous vehicle says, okay, I can extrapolate from their path that they're motionless, so they're going to stay motionless, and I'm going to drive past them. In fact, what was happening was that person really wanted to cross the street and had the right of way and would have crossed, but then they were like, wait, that autonomous vehicle isn't slowing down at all. Yeah. Did that car make the right decision? I think pretty clearly the answer is no. And there's a pissed off pedestrian and scared passengers in the car who would both agree that that answer is no. So really what you need to know is not where is this person going to be 2 seconds from now, but what's in that person's head that I need to think about when I'm making driving decisions. And that's what we enable.
So is there a lot of regional difference with this type of, sort of, if you're trying to predict this behavior or get a better understanding of what's in their head and their future movements, is it regional to the point of within a same country, or is regional more based on country to country? Can you tell a little bit more about what you found out there?
Yeah, that's a great question. It varies both within countries and between countries, but not necessarily in the ways that you would expect. So we've designed our system kind of with this in mind, right? So we knew from the beginning that if we wanted to deploy this system in, let's say, Delhi or Mexico City, kind of no matter what, the way that these interactions work is going to be different from the way that these interactions work in Boston or in San Francisco. What we found is that that's true, but a much bigger driver, in most places, a much bigger driver of differences in behavior is the built environment. So for instance, we have models that are trained to work on the US East Coast, primarily with data from the US East Coast. If you take those models to Southern California, they work okay, but they could actually use tuning. And the reason is not necessarily because people have different kind of social mores and different ways of understanding each other in California, although, I lived in California, that certainly to some degree that's true. But a big part of it is just that the roads are wider and the speeds are faster. So if there's someone who's standing next to a crosswalk that's an unsignalized crosswalk and they're trying to figure out if they can cross the street, whether or not how they make that decision varies a lot if the car is going at 45 miles an hour on a 4-lane road versus 20 miles an hour on a one-way street.
Yeah, I can see that definitely. Just the differences between California and Arizona. One of them, the drivers are slowing down, seeing you considering crossing the street, and the other one, they're speeding up because they're seeing you're considering to cross the street, and they want to keep you on the sidewalk, right?
One of the things we thought about explicitly, so we have right now, our model has 2 outputs, intention, which we've been talking about, which is, does this person want to cross in front of your car, and awareness. And we define awareness pretty specifically as, does this person know that your car is there? One of the reasons we did that is that we knew from experience that when people cross the street in Boston, as a pedestrian, it's very common to kind of intentionally not look at the driver of the oncoming car, because you're doing this little dance. Like, obviously you want to know if they're going to stop, but you don't want them to know that they know you're there, because then they're more likely to stop. And so kind of picking up those subtle social dynamics is baked into the way that we think about asking these questions.
Yeah, that's really interesting. So talk about psychophysics a little bit. How does that fit in? Where does that term, I'm not that familiar with it, so I'd love to hear how this ties in.
Yeah, absolutely. So that term, I'll tell you, I didn't use that word for the first 3 years of the company's existence, because I knew no one knows what that means. And then it slipped out in one conversation with a reporter, and he said, "That's such a cool word." I was like, "Oh, well, maybe, all right, no one knows what it means, but it sounds really good. So okay, let's lean into it." So psychophysics is a method in human behavioral science for studying how people perceive physical things about in the world, right? So it's kind of the psychology of physical thresholds. And what it really does is it allows you to take human vision and explore that using parameterized methods, so using variables. And so, for instance, if you want to know how people recognize a face, right? So if you show people a picture of a face, they will instantly know it's a face. They're 100% good at this. You can even pumpkins that kind of look like faces, they'll call them faces. So what's going on? So one thing you could do in psychophysics is you could say, okay, well, we're going to take a black bar and we're going to cover progressively more of the picture with this black bar, and we're going to see what happens to people's responses. And then you do the black bar, let's say you do it from top to bottom, then you do it from left to right, you do ones at random angles. And what you end up with there is that you say, okay, well, by changing this parameter of this black bar and how much it's covering and what angle it's at, we can change how good people are at recognizing faces. And then you can back out of that and you can say, okay, well, is that because of how much of the image is being covered? Is that because specifically the eyes are covered? And so it lets you, without having a strong prior guess at what visual features people are using to do something different, it lets you capture a lot of information about how people look at the world. And so when I talked about the way that we train models and how we don't treat the labelers as a black box, that's really what I mean. We're using the techniques of psychophysics in order to extract all of these visual features that people use to make these judgments about pedestrians that they couldn't tell you that they're using. And so turning these knobs and fiddling with these parameters lets us capture in a really rich way that mapping between making a guess about what somebody's head and what that person looks like.
That's interesting. How narrow would you say, obviously, you're in one specific area, but how narrow would you say are the findings? Are you actually able to glean additional insights that are applicable or useful for other purposes, or it's really very narrow to a human near a street, for example, and doing things that they would do around a street and other cars?
So the approach is pretty generally useful. We are doing level 4 robotaxis right now because they really need this, right? If you have a level 4 vehicle, and I think frankly they're realizing this, if you don't have something like what we're providing, you can't deploy in the places where you can make money. We were talking about Arizona earlier. Waymo's in Chandler, Arizona, and I think they're making amazing progress and it's a cool deployment. But I think one of the things that's notable about Chandler is it's not super pedestrian heavy. And that's very much on purpose. So that need is very stark in robotaxis, which for us as a company that really needs a lot of feedback and a lot of interaction with customers to learn things is very helpful for us. But this general approach really applies to any kind of nonverbal social interaction between an autonomous system and a person. You could think about warehouse robots, factory robots, sidewalk vehicles, automated crowd monitoring tools, all of these kind of insights are important. In terms of the specific experiments we're doing, I would say that the insights we glean tend to be fairly, all we're looking at is pedestrians and cars, so they tend to be fairly tied to that. But we definitely have come up with insights that were surprising, right? And we've learned things about how people carry themselves and how people, how this nonverbal communication works that never would have occurred to me in advance. And I can give you one example that I love to talk about. After we trained our first models, and these are our intention models, right? Whether someone wants to cross in front of the vehicle. We did an exercise where we went and looked at what parts of images our models cared about. So you can, do kind of a heat map. And if the neural network really cares about a certain part of the image, it will light up super bright. What we noticed is that our models lit up super bright. Anytime someone had a bag on their shoulder, it would really pay attention to the bag. And it was like, well, why is this like some weird thing? Do we have like does our training data have an overrepresentation of people crossing roads with bags versus not? And what we realized is, no, it's not that. But if you think about somebody with a bag on their shoulder that is thinking they're about to start crossing the road, and you have that just on one shoulder, what do? Well, you just kind of cinch up ever so slightly so that when you start moving, the bag doesn't go flying everywhere. So there's this little bit of tightening, and it's a very subtle visual feature. But in retrospect, of course, that's super diagnostic. And of course, we use that as humans, right? But that insight really came out of how we collect this training data, how we train these models. If you'd asked me in advance to, write down what are the visual features that people use to make these judgments, I never would have said, how tightly somebody has a bag cinched to their shoulder.
Yeah, that's really interesting. So you talked about sort of features and how you're analyzing and using a neural network. What do you think some of the biggest challenges are on the more of the technical side for you to be able to really sort of advance your AI and continue to evolve your technology?
So for us, I would say, first of all, what we're doing is something that, and I maybe if I'd realized this a little bit better before I started the company, it would have changed the issue. But this is very, very hard. We're taking machine learning research that's very much at the research frontier. And the point is to take that and get that all the way to a module that's reliable enough to be deployed in a vehicle. And one of the pieces of that that's really important is the question that we are asking. And we talked a little bit about this earlier, but the question we're asking, which is what's in that person's head right now as that relates to the task of driving, is very different than the kinds of questions our customers have typically asked. So for us, we've had to do a lot of work and build up a lot of expertise so that we can make sure that answering that question in these sort of critical moments when you have a difficult interaction with a pedestrian is reliably and correctly the information that you need to change the behavior of the vehicle. So what that means in practice is we really have to be the experts in how you integrate a system like this, how you use the outputs, how it should modify the motion plan, even questions of what the motion plan of the vehicle should be. We've had to develop a lot of expertise in those. And so I think that as far as the core model goes, it does what we say it does, right? Like when I gave you that 500 people in the car kind of analogy, that really is what it does. And it really does do that with a high degree of fidelity. But making sure that then we can take that and we can say to our customers, okay, this is where you plug it in. This is how you plug it in. This is what the output should look like. And if the output looks like that, you absolutely can rely on it, has been a substantial amount of effort and something that where we know how to do it now, but making sure that we can do that broadly is kind of the next step of our commercial relationships.
Yeah, I mean, it always comes down to implementation and sort of usage, and it's great. I've started a lot of companies, and oftentimes it's using data science to find some sort of opportunity. And you always think about it in the abstract, where once we get this in the market, it's amazing. It works really well, but then there's all the other pieces, and for it to really work, it's all about that integration. And what you guys are doing is so much more. The teams you're working with have to understand what you're doing as much as you have to understand what they're doing so that it can actually do what it's supposed to.
Absolutely. And I think that, the good part is that we've had a lot of time and a lot of iteration with customers to figure that out, right? So we have those answers now. The other part, I would say, I don't know that this is universally good, but it's helpful to us, is that you need this, right? So not just us, but our customers really need the answers to these questions, because without answering a question, being able to answer questions very much like the ones that we're answering, nothing else works. So there's a lot of incentive on both sides, and we've been able to do a lot of work to build out the infrastructure for that. But it absolutely, very early on, we would go to customers and they would say, well, how do we integrate this? And I would be like, well, however you want. And isn't that great? Just, what do you think? Like, I don't know. So kind of building out that, and really a big part of our team now is oriented around making sure we can answer those kinds of questions for customers, because certainly that's what appropriately they need from us.
Yeah, that's great. Before we go, I would like to ask you, what sort of guidance or advice would you give to someone who's seeking a career really in data science and engineering? Are there specific things from your background? You had a very unique experience, clearly, as far as your
right.
order of things. But I'd love to hear from you if you have some guidance to people who want to get deeper into it.
Yeah, well, I'll tell you. So I'm gonna say something, and I'm not completely sure that this is actually good practical advice, but it's my strongest intuition about what's happening now in machine learning and AI and computer vision is that the hard problems are no longer computer science problems. So if you think about training a deep network, and we get lots of people applying, and they're applying because they want to train deep networks. Frankly, training a deep network per se is pretty easy. Give it a data set, you feed it to it, you learn how to evaluate it, you learn how to do your optimizations later. there's kind of a cookbook for it, and it's not that hard. On the other hand, knowing how to ask questions that other people don't know how to ask with data, and knowing how to think about data in terms of when you need quality, what quality means, and sort of thinking about the rest of the workflow outside of the model training per se. There's some very, very interesting and very, very hard underexplored questions in that. And those really aren't computer science questions. They resolve to behavioral science questions, to infrastructure questions. So I would say my advice, such as it is to have kind of more than one. Don't just know about machine learning. Don't just learn about data science. Have something else you know and other things you know about the kind of penumbra of the questions and the answers that people are likely to be interested in.
Yeah, well, that's great. Always bringing more to the table helps in a lot of different situations. So thank you for that. Thank you for being a guest on the show today. We really appreciate it. Where can the community find you? What's the best way for the data science community to sort of reach out and connect?
Absolutely. I mean, I would say check out www.perceptiveautomata.com. We have a lot of information up there, including some nice visualizations of the black box metaphor we discussed, as well as job opportunities and a bunch of different ways to learn more.
Okay, well, great. At the Data Standard, we're a community of data enthusiasts and data thought leaders. We look forward to engaging with you on our website, datastandard.io, where we regularly post a wide range of podcasts with data executives and offer regular networking opportunities. For more information, visit the website. Thanks so much, Sam, for joining us today.
Thanks for having me.